Ladies and gentlemen, let's continue with our lectures in heat transfer. We're using the textbook of Cengel and Ghajar, and we've already completed chapter 4, the chapter on transient heat conduction, then also chapter 6 on the fundamentals of convection, and it is the introductory chapters to 3 more chapters that follows. Chapter 7 on external forced convection, which we've completed. Chapter 7 on, chapter 6 was on the fundamentals of convection. Chapter 7 was an external forced convection. Today we start with internal forced convection, chapter 8, and the next chapter will be natural convection. So there are 3 parts of it. In terms of chapter 8, internal forced convection, let's continue with that. And by way of introduction, what we're going to start with is some nomenclature. Nomenclature which will typically be used in this chapter, which will refer to pipes, ducts, conduits, tubes, etc. And the question is now, what is the difference between a pipe, a duct, a conduit, and a tube? These are being used interchangeably, and through traditions, certain people prefer to use certain nomenclature for some of these elements. For example, specifically the circular case. If the geometry is circular, like that, and if water flows through it, then there are some people that would say if it is circular and water flows through it, then we will refer to it as a pipe. Okay. Then there's another category of people that said, well, no, actually there's a difference between pipes and tubes. A pipe is where epsilon divided by d is a significant value, while for a tube, so that would be for a pipe, and that would be for a tube. For a tube, epsilon divided by d is approximately equal to 0, which therefore means it is a smooth tube. Okay. So if you use this as a definition, and you're going to do a design, and you're going to use tubes or pipes, circular in terms of cross-sectional area, then you're going to wonder, well, is it now a tube or is it a pipe? And when is this value significant? Well, in terms of the experiments that we've done in our lab, we have actually found that almost everything that you can buy these days are tubes. For all practical purposes, they are so smooth. You can go and measure the roughness, and you divide it by the diameter, and it is something like 0.4 zeros to 5 zeros before there's a number. So for all practical purposes, you can refer to them as tubes. It started with this nomenclature when, in the old days, pipes were casted. So they were casted, we don't do it today, and they were therefore actually quite relatively rough. And this is why this distinction between pipes and tubes have now started to sort of disappear, and people do not use these definitions to distinguish between pipes and tubes anymore. Then another type of cross-sectional geometry that you can get is one like that. Normally it is made from galvanized sheets, and it is specifically being used in the HVAC industry, the heating, ventilation, and air conditioning industry in buildings. That is how you get the cool air that is being distributed to all the venues, and these same types of geometries are being used to remove the hot air and take it again to the evaporator where it is being cooled. Normally, these on the pressure on the inside would be something like 120 kPa, while the pressure here on the outside would be typically atmospheric, 100 kPa or something like that. So therefore the pressure difference over the wall is in the order of about 20 kPa, which is very low. And although it is that low, you must remember these ducts are usually very large. So the surface areas are very large, and if you've got 20 kPa working on 1 square meter, it is 20,000 newtons of force that you actually have on that area there. So with pipes and tubes, normally we can use these and we can have pressures in the orders of megapascals. 20, 30, 40 megapascals is nothing unusual. So usually pipes and tubes, the circular area has the advantage that it can take very, very high pressures, while normally these types of ducts from galvanized iron are being used for low pressures. But in general, when you're going to do this chapter, normally enough information will be given so that you can figure out the cross-sectional area for the specific geometry. Okay, so in terms of internal forced convection, what is now different from external forced convection? That is what is important. And to do that, let's look at typically what happens in chapter 7, what is happening now in chapter 8 that we're going to do now, and what is going to happen in chapter 9. What are the different foci in every one of these chapters? So in chapter 7, the foci was typically on one or other area, like that of a flat plate, and we will have a boundary layer that's going to develop there. And the one boundary layer is going to be that of the velocity boundary layer, and the other one is going to be the thermal boundary layer. So let's suppose that is the velocity boundary layer, and there's the thermal boundary layer, and that is the free stream velocity. Okay. In this category of problems where we had external convection, then the Nusselt number was a function of Reynolds number and Prandtl number. Okay. What is now different with internal forced convection is that, again, boundary layers are going to develop, but normally, or in many cases, the two boundary layers are going to meet each other. Okay. While here, this boundary layer can grow infinitely. As long as this is a flat plate and you've got flow over it, the boundary layer is going to increase in height. So there's no limitations in the height. With internal flow, the limitation is that one there. However, normally the boundary layer grows from that side also. So normally they sort of meet in the middle. So again, in this chapter, the Nusselt number is going to be a function of the Reynolds number and the Prandtl number. And then chapter 9 is going to be on natural convection. And in natural convection, if this is a tube, then we are going to take into consideration that if there's heating or cooling, that there is going to be a temperature difference between the wall and the center. And that temperature difference is going to cause the flow to do something like that. We call that secondary flow. So while the flow is flowing in that direction, it will also circulate because of the temperature differences between the wall and the center. And then you're going to see that the Nusselt number is not only a function anymore of the Reynolds number and the Prandtl number, but it is also going to be a function now of the Grashof number. And the Grashof number we will define later on. So the Grashof number takes into consideration the temperature differences between the wall and the mean temperature. So in terms of this chapter, which is now on internal forced convection, there are many applications for this. I've now shown typically two plates which are parallel to each other, or it can be a tube, but it can be the inlet to a gas turbine engine. It can be in the combustion chamber of a gas turbine or an internal combustion engine, can be in the radiator of your car engine, can be in the air conditioning and refrigeration system with the refrigerant flowing through all the tubes. Many, many applications where we have internal flow and not external flow. Now with internal flow, normally there's also heating and cooling because the walls are at a higher temperature or a lower temperature than that of the fluid. But in general, what we are always interested in when we look at internal forced convection is to get the friction factors and the heat transfer coefficients. Those are the two things that we are interested in. The friction factors we need so that we can determine the pressure drop, and the heat transfer we require so that we can get the heat transfer rate. Normally the pressure drops with external convection and internal convection cost us money. Normally you need a fan or a pump to ensure that you've got flow through this geometry. Paragraph 8.2 is on the average velocity and temperature. Average velocities and temperatures. Let's look at, if you can divide your page in two, I'm going to do on the left-hand side, I'm going to do the average velocities, and then on the right-hand side, the average temperatures, so that you can see the similarities between the two. So, if we look at internal flow, these two lines are parallel to each other. They don't have to be. I've just drawn them like that. What we are normally going to do is, although we know that there's a velocity gradient there on the inside, if it's a tube, a circular tube, then we know, and the flow is laminar, then that would be a parabolic velocity profile. Now, to make things easier, although we know that in the details of this velocity profile is going to develop so that that velocity is Vmax, and this velocity is going to be V average, and the maximum velocity is actually 2 times the average velocity, although we know that. And from your fluid mechanics, you can also do the integration of the mass flow rate, which is equal to the density multiplied by the average velocity, multiplied by the cross-sectional area, and you can do this integration over the area of rho u r dr, rho u of r multiplied by d of the area. Although we can do that based on the mass flow, what we are normally going to do with internal convection is we are going to work with the average velocity. Although we will always know that there's a velocity distribution, we will work with the average velocity. And normally, if somebody gives you detail on any problem on internal convection, they're going to give you the mass flow rate going into the geometry. And it would be very seldom that somebody is going to give you the velocity. So based on the mass flow rate and the cross-sectional area, you can determine the average velocity, and using that average velocity, you're going to determine the Reynolds number. So that is just to make things simpler. The same is with the temperature distribution. With the temperature distribution, we are going to have, if the wall is at a higher temperature than that of the fluid, and if that is equal to the temperature, remember it's not a vector, I'm just using that line, the length of the line to indicate the temperature, and the longer it is, the higher the temperature. So if the wall is at a higher temperature than that of the fluid, we're going to have a temperature distribution like that. But now, we have to remember that although we've got this temperature distribution, the energy is being transported by the mass flow rate multiplied by its temperature, which means that you have to take into consideration the velocity profile to get the average temperature. And the fancy mathematics for that, the derivation of it, you can go and get in your textbook, but it is about the mass flow rate, Cp multiplied by a mean temperature, where the mean temperature is going to be typically that temperature there, Tm as the mean temperature, and that is going to be Ts, the surface temperature. I'm not going to do the full derivation for you, it is in the textbook, but based on that you can actually determine the average temperature, which is equal to 2 times V average R square, integration of 0 to R, of the temperature as a function of R, of UR multiplied by R dAc. Okay. So if we've got the velocity profile, we have to take into consideration the velocity profile and the temperature profile to get the average temperature. Very seldom that we're going to do that, but just think about it and always take that into consideration. In general, we are going to use this average to determine the Reynolds number. So the Reynolds number is equal to rho multiplied by V average multiplied by D divided by the viscosity, or you can also write it as the velocity multiplied, the average velocity of course, multiplied by the diameter divided by the kinematic viscosity. Okay, let's say that is equation 1, and then we take into consideration that the mass flow rate is equal to rho multiplied by the area and the average velocity. Then the average velocity is equal to the mass flow rate divided by rho, the cross-sectional area. And then for the special case, take note, for the special case of the area, which is equal to rho pi divided by 4d squared. For that special case, if we now take this velocity and we put it into that equation for the Reynolds number, then we can write the Reynolds number as 4 times the mass flow rate divided by the viscosity pi and the diameter. This is equation 8.5 in your textbook, and if I'm you, I will highlight this equation. Coming back to what I've said, that is that normally with internal convection problems, it will be very seldom that somebody is going to tell you what is the velocity going through the geometry. Normally it will be the mass flow rate. If you've got the mass flow rate, you can very quickly determine the Reynolds number. Otherwise, you must always go and calculate the velocity first. Okay. So it just saves you time. However, you have to write next to it, it's a special case for cross-sectional area. It is not a general equation valid for other cross-sectional areas, then it's not going to work. Okay, so please take note of that. It's really going to save you a lot of time in the tests and exams. Right, coming back to the different geometries. The different geometries that we can get normally with internal convection problems can be that of a smooth tube, if you've got something like that. It can be a square duct. It can be a rectangular duct. Or it can be a channel. Okay. And the fluid is obviously going to be in there. And in this case, it will only be there. Now, for all these cases, if we've got a heat transfer type of problem, and we want to get the friction factor and the heat transfer coefficients, we need empirical information, which can be in the form of a graph or it can be in tables. Which means that you need a lot of information. In some cases, you can get away by doing something different, for example, by using the hydraulic diameter. Okay, so the very simple explanation of the hydraulic diameter is that anything that's not circular or round, you're going to make as if it is round. Okay? And you've done it in fluid mechanics. So any geometry like this, by using the hydraulic diameter, you can, from there on, use all the empirical information or the information that you can get in textbook as if it is a circular tube. So that is what you can do with the hydraulic diameter. As you know, the definition of the hydraulic diameter is 4 times AC divided by P. Now, although this is the definition, you have to be very careful in terms of it's a reference to what area you're referring to and what perimeter you're referring to. And this is where many people confuses the application of the hydraulic diameter. So, for example, this is the cross-sectional area of the flow. Okay? And this perimeter is the wetted perimeter by the surface. Wetted by the surface. Let's look at a few simple cases. Let's suppose we've got a square duct of A by A, and the fluid is all around. Then the hydraulic diameter is equal to 4 times the cross-sectional area of the flow. Okay? And that is equal to A multiplied by A. Do you agree? Divided by the cross-sectional area of the wetted surface. This surface is going to be wet, that one, and that one. So it's 4 for A. A plus A plus A plus A, 4 times. So that is for the circular duct. If it is rectangular, AB, and take note, I fill it up all the way, then the hydraulic diameter is going to be 4 times the cross-sectional area of the flow is AB, and then the wetted perimeter is this length plus that one, plus that one, plus that one. So it is 2 times B and 2 times A. Is that clear to you? Let's do now the case for the channel. And this is where the application of the hydraulic diameter in many cases is not correct. So that length is A, that is H, and that is the fluid, and that is equal to B, that length there. Then the hydraulic diameter is equal to 4 times the cross-sectional area of the flow, AB. I see many of you are shaking your heads. You're right. It is not 4 times AB. It is 4 times HB. Because it is the cross-sectional area of the flow, okay, divided by the wetted perimeter, and the wetted perimeter is now H, plus B plus H. Okay. Because this surface there doesn't touch any of the perimeters. You happy with that? Okay. Not that we're really going to use this much. Normally you'll get this a lot in civil engineering, not that much in mechanical engineering. We prefer all our tubes to be full and not half full or something like that. The other one that we're actually going to use a lot is the annulus. Okay. This one, where the flow is between two tubes. So that part is where the flow is. And that is di, the internal diameter, and that is d0, the outer one. Now the hydraulic diameter is 4 times the cross-sectional area of the flow. It means it is that cross-sectional area there. So it is 4 times pi divided by 4 d0 square minus di square, like that. Okay? I'm going to say again, it's that cross-sectional area there. Okay? Now, divided by the wetted surface. The wetted surface is going to be firstly this surface here on the inside, which is going to be pi divided by 4 d0 square. Okay. Good, you're awake. Pi multiplied by the outside diameter. Okay, minus, not minus, sorry, plus pi multiplied by the inner one. That area there is also weight. Okay? Now the 4's disappear, the pi's disappear, and we have d0 square minus di square divided by do0 plus di, and we can write that as the outside diameter minus the inside diameter. The hydraulic diameter is equal to the outside diameter minus the inside diameter. Okay, are you happy with that? Good. Paragraph 8.3 is on the entrance region. And there's going to be 2 entrance regions. The one is going to be for the velocity profile. So if that is the tube, as I've discussed with you, with internal convection, you're going to have a boundary layer that's going to become thicker and thicker and thicker, and at a stage they're going to meet each other. So if this is equal to the inlet velocity, if that is equal to V average, okay, then all the flow outside the boundary layer is going to not even know about the boundary layer, all on the outside. So that velocity is still going to be that velocity there. Then it's going to decrease to the wall, okay, up to the point here where the velocity boundary layer is fully developed. Now I'm drawing it as if it is for laminar flow. It means that if we go downstream, the velocity distribution is going to be exactly the same. It's going to be like that. So in blue, I'm going to draw the velocity boundary layer. So that distance there is delta, the velocity boundary layer. If we go and plot now the friction factor as a function of x. So x is now measured from the inlet. Then this point where the two boundary layers meet is a very important point, because it means from this point onwards the flow is fully developed. If it's fully developed, the gradient there at the wall is going to remain constant. It cannot change. It means that from this point onwards, the friction factor is a constant. Okay. And before that, specifically at that point there, it is at its thinnest, which actually means the friction factor there almost goes to infinite. So it will do something like that. Here, the friction factor is a function of x, distance from the inlet, until it is fully developed. So we are going to refer to this boundary a lot. And downstream of this point, we are going to refer to the flow as fully developed. And on this part, we are going to say the flow is developing. It's developing, it is not fully developed. Here the flow is fully developed. This distance is known as LH. The length, how long it will take before the flow is hydrodynamically fully developed. In general, the friction factor is directly proportional to 1 divided by the boundary layer thickness. And if the flow is laminar, then this distance LH is equal to 0.05 multiplied by the Reynolds number multiplied by the diameter. And for turbulent flow, if the flow is turbulent, LH is 10 diameters. Just 10 diameters, then it is fully developed. Why is this important? Again, it is important because we always want to know what the friction factor is so that we can calculate the pressure drop, which is equal to F multiplied by L divided by D, rho V squared divided by 2. In general, when the friction factor is equal to a constant, it means that du dx is equal to 0. The velocity doesn't change anymore as a function of x. Right, now let's look at the similarity with temperature, with the thermal boundary layer. So again, for that same tube, we are going to have the thermal boundary layers that's going to meet. And for that, I'm going to use the rate. Okay. And that distance now is delta T. So if I can try to make a good drawing of the temperature profile, here at the inlet it would be an uniform velocity, uniform temperature profile. Then, if the walls are at a higher temperature, we're going to get something like that. So here on the outside, between the two boundary layers, this temperature will remain constant because they do not experience the boundary layer. Okay, so that is what's going to happen there, and then it's going to increase like that. So that is typically how the boundary layer develops until at this point here, where the temperature profile is going to do something like that. And then downstream of it, it's going to remain exactly the same temperature distribution. So if we now look at the heat transfer coefficient as a function of x, then again, where they meet determines when the flow is developing and when is it fully developed. Fully developed from there on, and on this side the flow is developing, and this distance is known as LT, the length before the flow is fully developed thermally. And our heat transfer coefficient is going to do something like that. From this point on, it's going to be a constant. So here the heat transfer coefficient is a constant. Here it's a function of x, it is still developing. And in general, the non-dimensionalized temperature, ddx of Tsx minus Trx divided by Tsx minus Tmx is equal to 0. It looks complicated, but it's just a non-dimensionalized temperature which has been written like that, and it shows that from this point on the non-dimensionalized temperature do not change, it is a constant. In general, for our thermal boundary layer, if the flow is laminar, then the distance that it's going to take before it's fully developed is equal to 0.05 multiplied by the Reynolds number, the diameter, and guess what? The Prandtl number. Okay. So if you look at this equation, okay, and that equation, you can see it is exactly the same except for the Prandtl number, which means that this is actually equal to LH multiplied by the Prandtl number. You see? So whatever this distance is, if this distance is 10 meters, then you just take this one and you multiply it by the Prandtl number and you get that distance for thermally fully developed flow. For turbulent, it is again 10 diameters. Very easy. Both of them 10 diameters, then it is fully developed. Thus, in general, if we now look at the three possibilities for Prandtl numbers, a Prandtl number of equal to 1, a Prandtl number larger than 1, and a Prandtl number smaller than 1. So if this is the case of Prandtl equal to 1, and that is the Prandtl smaller than 1, and that is the case for Prandtl larger than 1. Okay, and if we look at those three cases if this is the case for the velocity distribution, there it is fully developed. It's not going to be that it's maybe on the direct, no it is actually. So if we look at this one, we see it is not a function of Prandtl number, do you see? It's just a function of a Reynolds number and the diameter. So if the Reynolds number are the same for these three cases, so the Reynolds is constant and the diameter is the constant for all three cases, then it's going to take a certain distance LH before the flow is hydrodynamically fully developed. If the Prandtl number is equal to 1, then it means it's the same distance for both of them. They're going to be at the same point. It would be fully developed thermally as well as hydrodynamically. If the Prandtl number is smaller than 1, then it means the flow is going to be thermally fully developed before it is hydrodynamically fully developed. While if the Prandtl number is larger than 1, then it's going to be thermally fully developed after it is going to be hydrodynamically fully developed. So if we look at these three cases on graphs, for the case of Prandtl equal to 1, the case of Prandtl smaller than 1, and the case of Prandtl larger than 1. And if for all three of them, there's the friction factor, so the graphs should be all the same. Friction factor, there you go. And for all three of them, that is going to be LH. LH and LH. And they are exactly the same. Can actually make them in blue if you want to show it is for the velocity distribution, like that. Right. Now, if Prandtl is equal to 1, it means that they're going to take the same distance before they are fully developed. It doesn't mean that the friction factor is equal to the heat transfer coefficients. It just means that this distance is the same. So, if that is the heat transfer coefficients, from there on, at the same point, the flow is going to be fully developed. If Prandtl is smaller than 1, it means we're going to have something like that. The heat transfer coefficient is going to be fully developed before the friction factors. While in this case, it's going to be something like that. From there on only, it is fully developed. Do you follow that? Okay. Now, one last graph that I need to discuss with you before we finish this lecture. And that is a graph which is in your textbook, and it is figure 8.9. And it introduces a very important concept where it looks at the Nusselt numbers as a function of x divided by d. X divided by d is just a non-dimensionalized length. And normally, when x of d is equal to 1, it means it is just one diameter into the tube. So x of d can be 1,000 or 10,000. Obviously, it's going to be 1 if the length of the tube is the same as the diameter of the tube. And it's going to be approximately 0 when it is a washer. Okay? An orifice would be x of d is equal to 0. Now, what this graph shows is it shows typically the results for a Reynolds number of 10,000. Okay. It shows the results there. But if you look carefully, you will see there are some dotted lines there. I'm going to describe it to you just now. And then it shows for a few Reynolds numbers where the Reynolds numbers increases of the results. And that is where x of d is 10, which means it is 10 diameters from the inlet. If it's 10 diameters from the inlet, then the graph does something like that. And again, there's a dotted line there. So firstly, forget about the dotted lines. What it shows firstly, and take note, this is for Reynolds numbers of 10,000 and larger. So this is for a Reynolds number of 200,000. So this is for turbulent flow only. So it shows that for turbulent flow, if the Reynolds number is 10,000, it will just take one diameter before it is fully developed. If it is 200,000, it will take about 10 diameters. And from there on, it will always be about 10 diameters. So it's always 10 diameters and less before it is fully developed. This is a distinction that we're going to start making in this chapter, which is very important, because it refers to as a Nusselt number, a T, and a Nusselt number H. Now, what's the difference between the two? The difference between this one is that this one is for a constant wall temperature. So the wall temperature remains constant all the time, while this one is for a constant heat flux. And we're going to do the mathematics of these two in detail, and they are very important. The constant wall temperature cases and cases of constant heat flux. And most of the problems in industry will be one of these cases. The constant wall temperature case would be, if you think of the air conditioning industry, all condensers and evaporators. During the two-phase process, when it condenses or when it boils, the temperatures remain constant. And those are typically the type of problems which we would say is a constant wall temperature case. The other case is a constant heat flux. That is a case where you've got a tube and you put an electrical current through it, or you've got an electrical coil around it, or there's a nuclear reaction that gives you a constant heat flux. It would therefore means the heat flux is typically 3 kilowatts maybe per square meter or something like that. But what it shows is that there's a difference there. Not big, but there is a difference, and we always have to take it into consideration. But in general, if the flow is turbulent, 10 diameters is a conservative value to use, and all flow is fully developed within 10 diameters. And take note, after 10 diameters, it doesn't matter what type of method is being used, independent of it, in turbulent flow. Ladies and gentlemen, thank you very much. That's the end of the lecture, and we will continue then tomorrow. Thank you very much.